Hey there, and welcome. Today, we're going to dive into something really cool. We're going to talk about what happens when different unpredictable things, random variables, all crash into each other. We'll see how we can actually make sense of their relationships and even build some incredibly powerful statistical tools right out of that seeming chaos.
So, let's start with a little riddle for you. What do traffic jams, flood warnings, and, say, financial models all have in common? Well, the answer is that they all depend on a whole bunch of interconnected, random factors, right? It's never just one thing. It's how all those uncertain pieces fit together that really tells the story.
So here's our game plan. We'll start by looking at what happens when these uncertainties collide. Then we'll get into the actual rules that govern their relationships. After that, we'll figure out how to measure that connection. And then, this is my favorite part, we'll actually forge some brand new tools from all this. And finally, we'll see how they literally shape our world.
All right, first things first. When uncertainties collide, this is where we take that huge leap from just looking at one random event all by itself to looking at a whole bunch of them happening at the same time.
Think about it this way. Asking what's the chance of rain? That's a classic single variable problem. It's useful for sure, but it's also pretty limited. The real world makes us ask tougher questions, right? Like, what's the probability of rain and strong winds? All of a sudden, you have to understand how two totally separate things behave together. That is a joint variable problem, and that's where things get powerful.
So, how in the world do we handle that? Well, we need a rule book, right? A set of rules that tells us how our variables get along. And that brings us to our second section, where we get to meet the joint probability function.
To put it simply, the joint probability function is the official rulebook. It is the mathematical function that tells you the exact probability of two or more things happening at the exact same time. This rulebook is, no joke, the foundation for everything else we're going to talk about.
Now, what's so cool about this rulebook is that it has some awesome features built right in. Marginal probability? That lets us take our combined view and just zoom right back in on a single variable if we want to. And then there's conditional probability. That lets us play what if. Like, okay, if we already know it's super windy, what's the new probability of rain? See? Super useful. Okay, so we have a rule book that describes the relationship. The next logical question has to be, well, how strong is that relationship? Let's talk about actually measuring that connection. And we'll do that by going from a concept called covariance to its way more famous cousin, correlation. So our first tool for this job is covariance. It gives us a number, and that number tells us the direction of the relationship. Positive means they tend to move together, negative means they move in opposite ways. It's a great start, but here's the catch. The number itself, say it's 243.7, what does that even mean? Is that a strong connection? A weak one? It kind of depends on what you're measuring, so it's not super intuitive. But we can do better. We can actually standardize this whole thing to make it incredibly simple. And that, my friends, brings us to correlation. And this is the absolute beauty of correlation. It takes that messy, complex relationship and just boils it down to a single, elegant number on a universal scale, from -1 to +1. That's it. It doesn't matter if you're measuring wind speed, stock prices, or the flow of a river. The scale is always the same. And this table just illustrates it perfectly. A correlation of +1, that's like two dancers moving in perfect, beautiful sync. A correlation of -1, well, they're still in perfect sync, but they're moving in total opposition. One steps forward, the other steps back. And a correlation of 0? Yeah, that's just two dancers on the same floor, completely ignoring each other's existence. And now for the grand finale of our journey. We've learned how to describe and measure these relationships. But what if we could take these variables and combine them? I mean, add them, divide them, square them, and forge entirely new, incredibly powerful statistical tools? Well, this is where we start building new distributions. So our first creation is the chi-squared distribution. You should think of this as the ultimate goodness of fit tester. It's the tool you grab when you want to know if the data you actually collected in the real world matches up with the theory you had in your head. So how do you build one? Well, you basically take a bunch of standard, independent variables, you square them, and you add them up. And what's it for? It's for testing if the data you observed lines up with the data you expected to see based on some theory. It's a reality check. Next up in our toolkit is the student's t-distribution. And this thing's claim to fame is that it's the essential tool for when you just don't have a mountain of data to work with. When you're dealing with a small, real-world sample size, this is absolutely your best friend. Its construction is pretty clever. It's a mashup of the building blocks we've already seen. But its main job is really simple. It helps you confidently compare the average of two different groups, even when your data is a little sparse. And our final tool is the F distribution. Now, while the T distribution is amazing for comparing averages, the F distribution is the go-to tool for comparing something else entirely, the spread or the variability of different groups.
It's also built from our previous tools, following a really smart logic. Its whole purpose is to answer a critical question. Are these two groups equally consistent, or is one all over the place and unpredictable, while the other is tight and reliable?
Okay, so we have covered a lot of ground. Let's bring it all home and talk about why these building blocks really truly matter. How do these statistics actually go on to shape our world?
Let's just quickly retrace our steps. We started by just observing single events. Then, we learned how to analyze them together using joint probability. After that, we found a way to measure their connection with correlation. And finally, we used them as literal building blocks to create powerful new tools. And it's so important to remember
That these aren't just abstract equations from a textbook. They are the quiet, powerful engines running in the background of modern life. They drive scientific discovery, they ensure the quality of the things we buy, and they support almost all of the data analysis that informs major business and policy decisions. Which really just leaves us with one final thought. Now that you know about the tools that we use to understand the relationships between all these uncertain things, take a look around you. What hidden connections and unseen patterns in your own world are just waiting to be discovered?